Welcome Algebra 2 students to our video introducing the logarithm as an inverse. Online textbook chapter 7, purple textbook chapter 8. Logarithms are very serious business. Let's jump in and start by talking about the exponential function. Basic exponential function is in the form y equals ab to the x power. A is a factor that can compress or stretch the function, possibly reflect it, and then b is that base, and then x is your exponent, and it's y equals b to the x, and again, you can have an a out front. So let's graph a couple of different examples. And we will start with the first one we're going to graph, which is y equals 2 to the x power. And then we'll graph a couple transformations. So 2 to the x power. So if x is negative 1, let's make a little table of values here. X is negative 1, y is going to be 1/2. If x is 0, y is going to be 1. If x is 1, y is going to be 2. If x is 2, y is going to be 4. And if x is 3, y is going to be 8. So let's go ahead and graph those points. Negative 1, 1/2, 0, 1, 1, 2, 2, 4, and 3, right there, 3, 8. Yep. And you see the growth, exponential growth. All right, you can see that this graph has what's called an asymptote, fun word, asymptote, all the way along this line. This is never going to reach, this function will never reach this line. It will never reach the x-axis because there's no way for this y to equal 0. It's impossible. There's nothing that I could raise this base to get a 0 as a result. All right, so that's the first one we're going to graph. And the next one we're going to graph, we're going to do a stretch. So let's change to red. And let me go ahead and let's see. Let me find some space here. Let's graph y equals 2 times 2 to the x. Well, everything is going to be twice as tall. It's a vertical stretch. So it makes everything taller by a factor of 2. So it doubles the height of each one. So instead of 1/2, when you have negative 1, it would be up at 1. Instead of 1, when you plug in a value of 0 for x, it would be at 2. Same thing, this one would double in height. And this one would also double in height, so that's as far as I'm going to be able to go. Whoop, that one got a little messy there at the end. Fix that. Right there. And steeper, even a little bit faster. We can graph a reflection. We can graph the basic reflection. How about y equals negative 2 to the x, or negative 1 times 2 to the x. All right, which would be this would be the same thing as saying right here, negative 1. Same thing right here, saying negative 1 times 2 to the x, because the exponent applies first. So that one would take the entire black graph and reflect it downward. So we're not going to be able to see a whole lot of that graph, but you can see where it's going. You can see where it's heading. All right, how about a horizontal and a vertical translation? Okay, how about y equals 2 to the power of x minus 4. So that's a horizontal translation. 4, that's going to take us, that minus 4 is going to take us 4 to the right. 4 to the right. So each point that would usually be, where the black ones are, they're going to be 4 to the right instead. So we take this, this first one right here. So if I plug in x of negative 1, we end up with negative 1, that's going to move our point 1, 2, 3, 4 spaces over to positive 3. This point right here, which is 0, 1, it's going to again move over 1, 2, 3, 4 spaces all the way over to here. So let's put that little green dot in there. So we have the same shape. I made it a little too steep there. We have the same general shape there. Ugh. Terrible, Miss LeCompte. Come on, get it together. Graphing is a pain. And you can see very clearly the asymptote thing happening here. I can't draw this any further over because it's really getting to the point where it's going to just touch. All right, let's do one last one. One more color. All right, let's get this purple color. How about y equals 2 to the x plus 2? We'll like this one because all that's going to do is take every one of the points that's on the black graph, the original function, and go up 2. So, up 2, so 1, 2 to there. Up 2, 1, 2 to there. Up 2, 1, 2 to there. Up 2, 1, 2 to there, and we know we're not going to be able to fit the next one. So it's the same shape graph, except it's just risen up 2. All right, and you can, of course, combine all of them together. Let's look at a summary. All right, let's look at a summary here. So we know about our about the stretch. That's A. If it's positive and greater than 1, it's going to stretch. If it's a fraction, it's going to shrink. And if it's negative, it's going to reflect. You got your horizontal translation here, vertical translation there, and of course your parent function. Okay, what's a logarithm? Okay, a logarithm. A logarithm base b of a positive number x satisfies the following definition. For any b greater than 0, and b not equal to 1, log base b of x is equal to y, if and only if the b to the y power is equal to x. It's a way to rewrite an exponential going the opposite direction. So log base b of x equals y basically is saying what exponent can I put on this b to give me this x? What exponent can I put on this b to give me this x? Let's do just real quick, a couple of quick examples with powers of 10, because the log base 10 is the most common one. So log base 10 of 100. That's asking, what power do I put on 10 to get 100? What's log base b? What base 10 of 100? 10 to the what gives you 100? 10 to the second power. Now I said I know I'd do a couple, but let's just go to the next slide because I think I did a bunch. Hold on. Yes, here we go. All right, so we're going to start with rewrite in logarithmic form. So look here, you got 100 equals, I'm writing and I didn't mean to write. Okay. 100 equals 10 squared. So 10 is the base. 10 is the base. So log base goes underneath it as a little subscript there. So log base 10 of, that's the number on the other side, the 100, is equal to 2. So the exponent is on this side of the equal sign. How about the next one? Log base 3 of 81 equals 4. Okay, I definitely did not obviously leave enough room for all of this. So since I don't like them getting crowded, I'm going to come up here. How about log base 3 of 1? Well, what power do I put on a 3 to get a 1? Well, that's a 0. All right, and then how about this one? Log base 2/3. Can you do that? Sure you can. Log base 2/3 of 8/27. Well, that's just raising both numbers to the third power. How about we evaluate some logarithms? So let's try some of these here. And actually, I'm going to jump ahead and try the easiest one here, which is this one all the way on the end. Remember what we're saying here, right? It's log base 2 of 2 to the 5th is 2 to what exponent gives me 2 to the 5th? Well, 2 to what exponent gives me 2 to the 5th? Well, that's just 5. Okay, so let's do another one that's easy. Jump over here. Log base 5 of 125. What do I raise 5 to? 5 to what power equals 125? Well, that question mark would be 3. All right, these two a little bit different, a little bit tougher. How about we'll do this one over here. Log base 8 of 32. So 8 to what power equals 32? So I'm going to write it like this using a variable. Well, I don't know, because 8 to the second power is already 64. So it's got to be a number smaller than 2 but bigger than 1. What we're going to do is make the bases match on both sides. So we're going to write 8 as 2, but it's 2 to the third. So 8 to the x is 2 to the 3x. 32 is 2 to the fifth. That means, if they're equal, that 3x must equal 5, and if I divide, x equals 5 thirds. How about this one? 64 to the x power equals 1 over 32. Well, that's odd. Let's change them both to powers of 2. 64 is 2 to the, let's see, 6th power? Yep, 2 to the 6th power. 32 is 2 to the 5th power. So 1 over 32, so 6x, sorry. 64 to the x would be 2 to the 6x. Sorry, so 32, 1 over 32 would be 32 to the negative 1 power, or 2 to the negative 5 power. How do I know that? Because again, 32 is to the 5th power. 2 to the 5th power is 32. So 1 over 32, 2 to the negative 5th power. So that means 6x must equal negative 5. Because if the bases, again, we said this before just to clarify, if these bases are the same right here, the exponents must be equal. So we set them equal and solve, and x is negative 5/6. Okay, so that's really all you're going to learn about logarithms in terms of evaluating and that sort of thing. We just have to look at some functions with them. Alrighty, this is the last slide of the video. So we're going to graph the exponential function y equals 2 to the x, and we're also going to graph the logarithmic function y equals log base 2 of x. And I know it says and several transformations, but you know what? We've had a long enough video, and I think you know how to graph by transformation at this point. So we'll practice that in class. Okay, let me pause the video and set up the graph. Oh, okay, sorry to get a little carried away there. But what we're going to do real quick is I'm going to go ahead and jot down a couple of ordered pairs on the exponential function so you can graph that quickly. And then we'll what we're going to do is use the inverse, the fact that they're inverses, to graph it, the other one, the logarithmic one. So we just need a couple of ordered pairs. So for example, if I put in, we've done this before, if I put in a negative 1 for, oh, wrong color. If I put in a negative 1 for x, I'm going to get a 2 for y, so there's one ordered pair we can use. If I put in a 2 for x, I'm going to get a 4 for y. If I put in a 3 for x, I'm going to get an 8 for y. And if I put a 4 in, I'm going to get a 16, and actually that's going to fit. So let me just write that under. There we go. All right, so let's graph those points. Negative 1. Oh, gosh, 2. This will come up. Don't screw that up. Negative 1 would be a 1/2. Sorry about that. So negative 1 for x, 1/2 for y, which would put me here. All right. 2 for x gives you a 4 for y, puts me here. 3 for x gives you an 8 for y. And a 4 gives you 16 all the way up there. And then we get this nice exponential curve. This one's, it's much easier to see what's going on there with that it's rising exponentially. Remember, it still does have that asymptote down here. It is not going to touch that x-axis. Now what we're going to do is we're going to reverse all those ordered pairs. So 1/2 for x would be negative 1 for y. 4 for x would be 2 for y. 8 for x would be 3 for y. And finally 16 for x would be 4 for y. So that should be easy to graph. 1/2 for x, negative 1 for y. So that's a little bit strange now, isn't it? So that means 1/2 for x, negative 1 for y. That puts us right there. 4, 2 puts us right there. 8, 3 right there. And 16, 4 right there. So we get, just as we learned about inverses, they are opposites. If I was to go ahead and graph this line, the y equals x line, you can see that They are perfect inverses. If I folded it over, the blue one and the green one would line up very nicely. And just one other key point here to remind you about, if we put in the value of 0 for x, remember that we're going to get 1 for y, so we should notice that 0, 1 also on our graph, and since we can reverse them, 1, 0 is on the green graph. And I wanted to make sure that you guys saw that on those functions. So I hope this didn't end up too long. I know you have 2 videos tonight. I know it sucks, but you had like a week off with snow days. So we got to try to catch up. All right, guys. See you in class.